Good afternoon, everyone. This is for finite math. Let's get started. Let me open up a new Word document. Let me, this is again for finite math. Let me get the font sufficiently big. Now, for matrices, you have, like you'll have a matrix of the form in two dimensions, 2 by 2 matrix, 2 rows, 2 columns. Again, you'll have a 2 by 2, which we know from last chapter how to do the dimensions. Now you'll have A, B, C, and D. Now, let's say, so we got a matrix like A, B, C, D. And imagine that A, B, C, and D are numbers. So let us say that A, B, C, and D are real numbers, which is what we usually do in algebra. And if we're lucky enough to where AD minus BC is non-zero, then well, something we can get a pretty value. We can raise this to the power of -1, and we will get something of, well, we'll get another matrix, but it's called the inverse. Now, how do we define the inverse? We define it as follows. We need to make some changes. We turn this into A. We turn this here into D. And we switch places. We negate these here and here. And now we do one other thing. So we got neg B, neg C, we got dA. And we divide each entry by AD minus BC. So we divide each of these by 8. Notice I insisted on AD minus BC not being 0, so there'd be no danger of me dividing by 0. So AD minus BC. So divide by AD minus BC. Now this matrix here is called the multiplicative inverse of this matrix, and again we're assuming that this AD minus BC down here is not 0. And in a very real sense, these are reciprocals of each other. These are reciprocals of from the old world. Okay. So, like for example, let's say that ABCD is, let's say I've got 3, 5, -1, and 2. And you can check AD minus BC. A times D minus B times C. That better not be 0. 3 times 2 is 6. And then minus, now 5 times -1. Well, that's 6 minus -5. That's 11. But all I really care about, that's not 0, right? So we're good to go. So if I want the inverse of this, now I want to find the inverse. I want the so-called matrix reciprocal. It's, the reciprocal is a little bit loose, but in a very real way, it kind of acts like the reciprocal acted in the old world of real and complex numbers. So, well, we just, well, that's fine, but I kind of want, I want to start doing my reciprocal, don't I? So let's do the inverse. Well, so I need to switch places with D and A. And I need to do neg B, neg C, don't I? And I need to do divide everybody by AD minus BC. And I wish I wouldn't have erased that now. What was it? It was it was 11, wasn't it? It was 6 minus neg 5, which is 6 plus 5, which was 11. Well, so AD minus BC is 11. So, well, now we just switch places with the 2 and with the 3, but now they're all over 11. And so I've got 1 there. I got neg 5 there. But I got to divide them by 11, don't I? I'm about to mess up on you. Sorry, guys. There it is. This is the inverse. Now, why do I call it the inverse? Because I claim that if I multiply it by the original, I'll come back where I started. So I claim that if the original was 3, 5, neg 1, 2, and I ought to have left a copy of the original, and I didn't exactly do that. So let me just, well, I got rid of my original. Oh well. So I've got 3, 5, neg 1, 2, and then I multiply that by. Now I claim that these are commutative. Remember, matrices don't have to be commutative at all, but inverses always will be. But there's something even nicer than that. They multiply to the identity 1, 0, 0, 1. We will get, if you multiply these out, like do row by column. Well, with you guys, I need to explain to you how to multiply matrices, don't I? So, well, if you multiply out, if I need to, how do you multiply matrices? You do from the long video last time. Well, you remember this consists of two covectors, two row vectors, and you do each covector times the column vector. So you take 3, you sweep across 3, 5, you do 3, 5, and you push it down this column here. So you do 3 first times first plus second times second. It's the inner product, or the dot product. So I do 3, we're going to get a 2 by 2 times a 2 by 2 is a 2 by 2. Remember from the long, you'll need to go back and watch the long video, but a 2 by 2 times a 2 by 2 is a 2 by 2. So we're going to get another 2 by 2. So that's good news. Anytime you multiply a square by another square of the same type, keyword of the same type, you'll get another square of that exact same type. Like a 3 by 3 times a 3 by 3 gives you another 3 by 3. A 2 by 2 times a 2 by 2 gives you another 2 by 2. A 4 by 4 times a 4 by 4 gives you a 4 by 4, and so on. Well, now, so we can do this. Remember, when you're doing matrix multiplication, you got to make sure you can do it. Like an m by n times an m by p equals an m by p. The first and the last. M row p column. But lucky for us, we are lucky. We just got a r by r. Well, we're lucky because we're just like a n by n times n by n, and there's nowhere to go. It's just n by n. So we are lucky indeed here. So special case, right? This is special. Okay. So now, in general, if you're not square, you have to do the n by n times n by p is m by p. But now we're lucky. Now you go 3 times 2 elevenths plus 5 times neg 5 elevenths. Okay. Now I wasn't supposed to switch the neg 1 and the 5, guys. I've been bad. Sorry. You only switch. Yeah, I was very bad. I'm supposed to negate. That was very bad. I'm supposed to negate. So it's dA neg B neg C. Yep. I said it right. I did it right in the abstract, but I was very bad here. So if you negate 5, you get neg 5. If you negate neg 1, you get positive 1. I was very bad. Now these, you just switch them. Okay. Now, oops, and I was very bad again. I've been bad. I've been very bad. So sorry, guys. And oops, I was bad. I was doubly bad. I did that again for the same reason. Now I'm good. Okay. And so 3 times 2 is 6 elevenths. You still need to watch that video, but so you got 6 elevenths, and then 5 times 1 is 5, but that's 5 elevenths. You just have to drag the elevenths along with it. But hey, guys, that's 1. That's just positive 1. Okay. Now you gotta stay across the covector 3, 5. Now 3 times neg 5 is neg 15 elevenths. And then 5 times 3 is positive 15 elevenths. But hey, this is just neg 15 plus pos 15. That's just dead and gone. They're over the same denominator and everything. So it's dead and gone. Now we've done our do with 3, 5. Now we jump down to the row vector, which I call a covector, neg 1, 2. Now a column vector is a real vector. So then we go down the first column vector, 2 elevenths and 1 elevenths. So neg 1 times 2 is neg 2. And then plus 2 times 1 is 2. But neg 2 plus 2 is 0. And then neg 1, now be careful, neg 1 times neg 5 is actually positive 5 after all. And then 2 times 3 is positive 6. But 5 plus 6 is 11 elevenths. But 11 elevenths is just 1. Guys, there I go. Okay, inverses multiply to 1. And we can identify this. This corresponds to, this is the identity. If you multiply any matrix, any 2 by 2 matrix by 1, 0, 0, 1, you will just get that matrix back, or the other guy. Like for any 2 by 2, like for any 2 by 2 matrix, call it J. J times the identity just gives you J all over again. And if you go backwards, it's the same. Identity times J is still J. J identity equals J. Identity times J equals J. It doesn't matter which way. The identity acts like the number 1. It behaves like 1. It behaves like the number 1 in the multiplicatively, right? It behaves like 1 multiplicatively. In other words, it's neutral and kind of meek and stoic, right? This guy right here, 1001. Well, it's meek but stoic, 1001. Like J times the identity equals the identity times J, which just equals J himself. And we refer to this guy, we're going to call this guy the identity. J times I equals I times J, which equals J. But technically, I need to go the other way, right? And it's going to be true the other way, but I do need to go the other way with it. I need to put the invert in front and the main guy in back and make sure it works the other way. And I can tell you it's going to work, but I need to just show you guys that it does work. So I got, so let me just plug it on down the line here. And I've got, 3, 5, neg 1, 2, like that. Okay. And this acts like the number 1 in multiplication. It doesn't change the original matrix. I'm talking about the 1001, that is. But anyway, let's show that this gives me the number 1, or multiplies to cough 1, which is the identity I. And I'm just going to go ahead and put this down here, and I'm just going to talk you through it and show that it's true. This is going to be true. But, okay, 2 times 3. Let's go across the covector here and down the main vector here. This is 6. Now, neg is pos. Okay, 2 times 3 is 6. And then you do neg 5 elevenths times the neg 1. But the two negatives cancel, guys. So that's positive 5 elevenths after all. So positive 6 elevenths plus positive 5 elevenths is positive 11 elevenths, which is positive 1 right here. So you have to cancel the double negative here and here, okay? And then now, and keep in mind, if you multiply row 1 here times column 2 here, you'll get entry row 2 you'll get entry row 1 column 2. So row 1 times column 2 will give you entry, for the solution that's in row 1 column 2, which is here. And the analogous thing is true for the others. You remember when we did row 1 column 1, we got what was in row 1 column 1, which was the 1. Now we're going to do row 1, column 2, and we should get 0, which because we're doing something else. Oh, okay. So now 2/11 times 5 positive is that's going to be what, 10/11. Now be careful. Then neg 5/11 times this 2 right here is going to be neg 10/11. But their pos and the neg kill each other, and we get 0 because we did now because row 1 was preceded by column 2. We get the guy that's in row 1, column 2, and that guy is 0 himself here. The 0 that I've got highlighted here. Now we're going to go snooping for the converse. We're going to go snooping for row 2, column 1, on the other hand. Well, as luck would have it, we're going to get 0 there as well. Now, they don't always match in general, but in this pretty case they do. Now, 1/11 times 3 is 3/11. Now, plus 3/11 times neg 1 is neg 3/11. But you do this times this plus this times this, and you'll get 0. Guys, it's really important you follow the motions. You go across this and down this to get this. Row 2 rather, column 1 gives you the guy in row 2, column 1 for the solution. Because the 3/11 positive adds to the neg 3/11, and you get 0. And then finally, 5/11 plus 6/11 gives you 11/11, but that's just 1. And because I did this, and it went down times this, and there we are. We got the identity again. So we get the identity going both ways. Now keep in mind, this was very pretty, and we got very lucky indeed with inverses, right? It always works this way. Inverses, when they exist, will always work this way. Let's see. Now keep in mind, let's not get spoiled. Keep in mind, however, that matrix multiplication does not commute for most things. Even in 2D, even for most 2x2 matrices. So matrix multiplication does not commute for most 2x2 matrices. However, it does commute. It does so for it does commute for special types of matrices. But just for these very special types. And I ought to put very, right? Because most of the time, you can forget about commutativity, guys. Don't count on it at all. Luckily, I will say luckily, associativity and distributivity I can't spell. Distributivity. Well, I could always spell so well now. Oh, it doesn't like the word anyway. Distributivity, I thought was a word. Associativity and distributive properties do hold valid so distributivity holds true, associativity holds true for matrix multiplication. So we get very lucky there, guys. We are all day lucky, okay? When it comes to that, we are all day lucky. With matrix multiplication and stuff like that, yeah, we are very lucky indeed. So you wouldn't think we would have associativity and distributivity, but we do. We get away with those, but we don't usually keep commutativity. I could cook up two things right now where commutativity would collapse. Like A times B, and B times A usually differ. Now with inverses, they don't. You'll get 1, 0, 0, 1. Of course, well, naturally, of course, JI. Now I everything has to commute. You'll just get the original guy, right? So I is very pretty. Now there is, of course, the zero matrix. Now the zero matrix is fatalistic. It's non-invertible, but commutative. It is a commutative. It is fatalistic. In a sense, it soaks everything up, because if you multiply, it acts like the number zero. Like 0 times anybody is just 0, right? Like the zero matrix, like times J will just give you J times the zero matrix, which will give you the zero matrix. Now 0 doesn't have an inverse, right? Zero just soaks everybody up. So, and there's weirdly, there you can, if AD minus BC equals 0, which is precisely when, by the way, this is precisely when matrices don't have inverses. These are kind of the bad guys. That you can dig up matrices. You can dig up matrices, non-zero matrices, such that, well, we'll call them, I'll give them names. Non-zero matrices, I'll call them big P and big Q, such that PQ, the product of P and Q, equals the zero matrix. That in the real numbers, guys, this didn't happen. And it happens now. This only happens with the non-invertibles, and I'll put a note. This only happens with the non-invertibles, and you get a non-invertible, which are precisely the non-invertible matrices, which are precisely those matrices for whom AD minus BC equals 0. AD minus BC equals 0 is actually nasty business, right? Okay. But yeah, you can, like I could cook up two matrices that would multiply to the zero matrix, even though neither guy himself is a zero matrix. That didn't happen in the reals. That didn't even happen in the polynomials. So that's kind of funny, right? That's kind of strange. Now, however, if you insist on, if you only consider the matrices, if you only consider the invertibles, the invertible matrices, this phenomenon, this will not happen, or this phenomenon will not occur. So matrices that are invertible can be funny on their own right, but they can be funny too, guys. Don't underestimate them, but they won't be that funny. They won't allow that kind of stuff to happen. Now, notwithstanding, even invertible matrices are strange. They are usually non-commutative. Commutativity has little to do with invertibility, guys, by the way. Commutativity and invertibility commutative and invertible are only loosely related. they have some relations, but it's very, 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 very loose. So don't get too. Commutativity and invertibility are very loosely related. Commutative just means AB equals BA. Invertible, that means A has an inverse. It has what you could think of as a reciprocal. It has an inverse B such that AB equals BA, which equals the identity I. So they're not really they're not strongly related. But anyway, indeed, you can find commutative matrices that are not invertible, and you can find invertible matrices that are not commutative. So really, the relationship is not strong. But anyway, now if you multiply two matrices, again, if you have m rows by n columns, now recall, well, guys, if you have m rows by n columns, and you, m rows by n columns, and you multiply that by a matrix that has n rows by p columns, you will get, it produces a matrix with m rows and p columns. If you don't have this set up, you can't multiply matrices. You can't do the multiplication. You just can't do it. Okay. Now recall, if you want to add matrices, they have to have the dimensions have to be exactly alike. Now recall that adding is different. Adding and subtracting matrices, the matrices dimensions must be exactly the same. This is different than multiplying, right? This is different than multiplying matrices. Because multiplying matrices, so recall, and how about, this is almost too concise. So recall, it's correct, but it's too concise. Recall that for multiplying matrices, the dimensionality rule is, and it's this guy right here. And now the word produces doesn't fit with good English anymore. So how about I do that? Okay. M by n, n by p. This, if you multiply matrices, you have to obey this rule. Now, guys, if it's a square matrix, everybody equals the letter n, as in Nebraska. And of course it's true. If everybody equals n, this can't help but be right. Everybody's good. And of course you can add and subtract because everybody's good. And one more thing, scalar multiplication. You know, like if you, and this comes in handy with that, you know how like it's kind of awkward writing AD over BC for everybody in the inverse? Sometimes you can just yank out a constant. Like if everybody is multiplied by 1 over AD minus BC for when the inverse exists, that gets old having to write it out that way every time. So for a 2 by 2, like for a 2 by 2, so we have A, we have B, we have C, we have D. Now, so I have this, and I have this, and so let me just show you a little trick, and just to keep things from just getting sort of out of control with it. Instead of writing, if we know the inverse, so we want to take the inverse. Now let's just agree. So Well, I'm trying to be economical. Now, what did we do again? We did D, we did A, we negated these. It's trying to keep everything straight here. Now, instead of going through and doing that to each and every term, there's a convention. You can do 1 over AD minus BC on the outside. And if we let say P equals, if we let just say big R, or big U equal 1 over AD minus, well, no, I better not be letting that. But that's true. Let's not go there. But so we have 1 over AD minus BC. You can just yank out constants, guys. So more generally, how about I just go back to ABCD again? So let's just say I multiply everybody in here by P, and P is just some multiplier. And even if it's 0, I can still divide it out, or I can't divide by 0, but I can still factor 0 out, right? So I can still just factor it out. Even if it's 0, just so I don't divide by 0, I can still factor out P, right? It'd be 0 wouldn't be any fun, but it'd be okay. So there, just factor out P. And now if you redistribute P back in, you have to multiply everybody in here by P. And this is called scalar multiplication of the matrix. Okay. Now, guys, so I've given you this pretty little shortcut for finding the inverse of a 2D. Unfortunately, it doesn't work so well for 3D. And so now, most of this stuff will boil over to 3D, except for the thing that I'd like to the most, the 1 over AD. Everything I've said for 2D is true for 3D. Everything, except for the 1 over AD minus BC, the way of finding the inverse. You've got to find the inverse of the 3D guy the hard way. Everything I said about identities, 99.99999% of what's true for 2D is true for 3D, but I can't use my 1 over AD minus BC guy anymore. I can find the inverse, and I must, but I've got to do it the old-fashioned hard way. It's the way I could have done for 2D. So let me motivate. What if I wanted to done 2D the hard way? I probably should have done it the hard way because I'm going to have to do 3D the hard way anyway. So, so here goes. If I'd wanted to find the inverse of ABCD the hard way, well, yeah, you're like, well, that's no fun. Well, and it's not. But I wanted to at least give you the pretty method is so nice to have, because when you're in 2D, you can't use it in 3D, but that doesn't mean that you should just shun it, or turn your back on it, because it's good to have, right? But guys, I got to pay my dues. So there's 2 or 3 ways I could write this. I'm going to put the identity over here. So let's put the identity, and we're going to think of this. We're going to divide the identity, cough, cough, divide the identity by the invertible, assuming it's invertible, A, B, C, D. And again, it's AD minus BC. We are assuming that that's not 0, but we can't take the easy way out anymore. And for 3D, we're not going to have access to AD minus BC anymore. So we're just going to have to play nice here. Okay, yeah, we had to be very careful. And like, what if we don't have the AD minus BC formula to fall on? And guys, I was tempted to use variables earlier, and actually, as I had to think about this a while, it's actually enough for AD minus BC to not vanish. But it takes a little bit of showing to really think that through. If AD minus BC does not vanish, you're in good shape, but you don't have to go single variable case by case. You don't have to say, well, is A 0? Is B 0? Oh no. Is C 0? Oh no. if AD minus BC is not 0, you're golden. You're good. You're good. You're fine. The thing about doing echelon here that makes it so dangerous, if I generalize this, if I want to do a nice little proof here, you're going to have to contend with B. As it turns out, you can rearrange this to where A and D, either A or D are not going to both be 0. We don't know. These could A could be 0 possibly, or D could be 0, but they can't both be 0. Well, they could be, but it would be kind of awkward. But like that gets nasty. You want to save the dividing. You can't go dividing. And I messed this up earlier. I had to cut out some video. And where I made the mistake was right here. You can't multiply by B because B could be 0. And like what I did was I started off, on a good enough foot. But really I started off on a bad foot because you don't know who your 0 term is. Like really you can't multiply. You got to add or subtract. So really I've had to edit this video, and it's been infuriating. It's driven me crazy. But I don't know who my non-zero term is in all this. And I'm going to have to, really the best thing you can do is just go ahead and divide everybody by AD minus BC. But I don't want to get into doing proofs, to be honest with y'all guys. We know AD minus BC is 0. Everything I've done is pretty much invalid. I'd have to do case by case, and I don't want to. I don't want to do case 1 or case 50, to be honest with you. If we're going to do it a way that it generalized to 3D, I may as well just do numbers. Let's say 2, 3, 4, and let's say neg 7. That'll be invertible. How about neg 1? That's invertible. And AD minus BC, that's 2 times neg 1. That's neg 2. And then 3 times 4 is 12. Neg 2 minus 12 is neg 14. So we're invertible. And guys, all my proofing down here, I hate to get rid of it. I hate like everything to get rid of it. And no, let's not talk about that. That's not true. I said some stuff that I had to get rid of. Now, AD minus BC not equal to 0 is true, but let's not talk about any invertible matrix can be roll swapped. That's true, but let's not roll swap it. I don't want to go there. You can't multiply by C because C could be 0. Everything I said goes out the window, and that hurts my feelings real bad. So we may as well let's just do a number example. What if I have a 3D system and I can't use this? Guys, for 3D, you can't use this little nifty inverse shortcut. So let me show you the long way to do it, and you can generalize this to 3D. So you write 1001 here, and you can think of this as divided by, and here's the guy I want to find the inverse of. So I want to find the inverse of, I want to find the inverse of 2, 3, 4, neg 1. 2, 3, 4, neg 1, and I want to find the inverse of it. So I want to find the inverse of this. And this is who I want to find, neg 1 power. Okay, so I can do this, right? AD minus BC for my original guy is neg 14. The point is it's not 0. Well, now here's the procedure. You want to get 1001 over here, and you want to get your main guy over here. And you'll do and this procedure works for 3 by 3 or 4 by 4 or any old square matrix you want to find the inverse of. Okay. Well, what you'll do, you want to get 1001. So let's just let's just eliminate row 1. Hey, it'd be nice to have neg 4 here. So let me multiply. Let's do neg 2 row 1 and put it in row 1. So that would be neg 4. 0 don't care. No, wait, neg 2. That's neg 2. Sorry, guys. That's neg 4. and then neg 2 times 3 is neg 6. And then now if I multiply this row, no, I don't want to. So what do I do? Oop, and that's a 1 there. So now I add them. I do row 1 plus row 2, and I put that into row 2, and I get, well, what do I get? Neg 2 plus 0 is neg 2. 0 plus 1 is 1. Neg 4 plus, remember, you want to kill all the terms that are off the main diagonal. So I want to kill that 4 to 0. And then neg 6 plus 1 is neg 7, because our objective is to get rid of the 4 and the neg 6. We want to get rid of the 4, of the pos 4 and the neg 6, because we want to get rid of the terms off the main diagonal for the terms on the right side here. Okay, we're wanting to make this the identity matrix. Okay, well, so we've killed the 0. Now we need to kill the neg 6. But now the 42 is our best shot here, right? And well, no, not really. Hey, I can clean row 1 back up, right? So I can do neg half row 1 and put it back in row 1 to clean row 1 back up. Control C. Oh, humbug. Bah humbug. 1, and then 2, and then 3. Let's see. Okay, guys, it's just, why did I do that? It's just easier to work with 3 than it is neg 6. Sorry I got quiet on you. I have to think when I'm doing this or I'll make a mistake for sure. Now, keep in mind, I don't want to kill these off diagonals, because this is who I want to mess up. This is actually who I want to clean up over here. Okay. Now. I want to kill the 3, but I've got to get a 21 of some kind to do it. So, now let's see, guys. The best you can do is just do 7 times the 3, 3 times the neg 7. So 7 times row 1, put row 1. 3 times row 2, hit row 2, and we get 7, 14, 21. Now 3 times this is neg 6, 3, and then neg 21. Okay, and then we, because I want that neg 21 below my 21's why I did all this. 7 hit 3, 3 hit neg 7 was why I did this here. Okay, then we add row 1 to row 2, and we're going to get, well, I want to put that in row 2 because I want, no, row 1, sorry. We want to put that in row 1 because we want this guy right here to die. So we get, or to be eliminated. Maybe I need to be less melodramatic. So come on. Go away. 0. 0 plus 14 stays 14. 3 plus 0 becomes 3. Neg 6 plus 7 becomes 1. Okay, we're getting there. I've killed my terms off the main diagonal, or eliminated them more appropriately. So we're getting there. Now we don't want to mess with these zeros. That's good, right? That's 90% of the battle. Now, well, I just divide by 7 up here. Divide by, no. I divide by 14 up here. I divide by neg 21 down here, and I'm done doing that. So I do, well, come on now, be good, be nice. I do 1/14 row 1. I put that into row 1, and neg 1/21 row 2, and I put that into row 2, and I get 1/14, 3/14, and the whole point was to get 1 there. 0 didn't change. I don't want it to. Now, divide by 21. Now, guys, neg 6 over 21 is cool, but what is neg 6 over 21? Reduce it, reduce it. That's going to be divided by 3, divided by 3. Now, 3 over 21 is cool, but what is that? 1/7. Now, 0 doesn't change. I don't want him to. 0 over 21 is 0. And, wait, I need to be divided by neg 21, don't I? Yikes. So, I need to change neg pos becomes pos neg. 0 stays 0. Now, neg 21 becomes pos 1. That was the whole point. I want pos 1s here, 0s here. Okay, now for the moment of truth and humility. Is this right? Did I make any arithmetic boo-boos? The procedure's correct. I'm going to tell you right now, procedure's correct. It's just a matter of did I make any arithmetic boo-boos or mistakes along the way? Maybe not. Let's see. So I claim that the inverse of my original guy, and this will work with 3x3 matrices, 4x4. It's just a lot longer, but this will generalize. Now, guys, will this work? What was my original guy? I forgot. That's pretty bad, huh? So I claim, so Control C. So for 2, 3, 4, neg 1, I claim the inverse of 2, 3, 4, neg 1 is, well, I claim that it is, if I can ever get over there, well, 1/14, 3/14, 2/7, neg 1/7, and so we got that, and I've got it saved as inverses. Okay, now I claim that, and I need to check that claim. Oh, brother. Now I need to copy down my original, and now usually if it works one way to, I'm not guaranteed, but usually if it works one way to work the other. Oops. So Control C, I need to do my Control V in down here. Okay, now go. Let's see. 2/14. Oh, now keep in mind, this is sevenths, right? So 2/14 is 1/7, and then 6/7 is 7/7, and I'm not just wishful thinking, that is 1. Okay, now 6/14, that is 3/7, positive, and this is neg 3/7, that is 0. I got to keep checking. Now this should be 0 as well. 4/14 is 2/7, and then neg 2/7 is 0. 12/14 is who? 6/7. Whoa. Okay, and then neg is okay. Neg is positive. 1/7. 6/7 and 1/7 is 7/7, which is 1 positive. Good. So it worked that way. And if I try to go backwards, if I try to go backwards, Control C, 99. Usually, 99% of the time it'll work. I do want to check it, integrity, you know. So this worked. I got my beloved identity 1001. But I claim that I'll get 1001 down here too. I can't get any room, and likewise, and I should get the same thing here too. And I should get one, and I'll let you guys fill it in. Convince yourself that I get the same thing here too, but you got to go. Let's see, that's 2/14, which is the 7th, plus 12/14. Well, 2/14. Leave it unreduced. Plus, if you want to, 12/14 is 14/14, which is 1. Sometimes you have to reduce it, or it becomes so muddy. 2/14, 12/14. Now 3/14 minus 3/14 is 0. Looking good. 2/7, 4/7, 0. Yeah. And then I'm almost all but the last entry. 6/7 minus a neg. It won. All good. Yep. It checked out. All good. Now this is generalized to 3D. Guys, I would have to almost sit here to do it in 3D. I mean, you can. there's technology out there. You know, there's alpha and Symbo and all that. But to do it in 3D, you do it the same way. To get an inverse in 3D, you do it the same way we just did it in 2D, guys. You're going to have to come on in. You're going to have to... Now, there is no AD minus BC to catch you. You're just going to have to hope. And if it's not invertible, you'll know it when you get crazy stuff at the end. But let's say I've got 2, 3, 2, 2. Let's say I got neg 1, 5, and 7 or something, or let's say 6. Let's say 7, 3, and 4, or whatever. Now let's say that I want to find the inverse of this, right? Let's say I want to find the inverse. Well, if I want to find the inverse, well, so to find the inverse, that's the -1 power. So what you do is you'll have to go to matrix. Be good. Hello again. Good morning, guys. I do declare, I think that these 3D matrices, this is like the 5th overdub I've done. I didn't. I was going to leave it to y'all to. I finally got this right. I checked it against Wolfram Alpha. I found the correct inverse. I did it on my own. I think I made minus sign. I did copy and paste, 2 or 3 copy and paste errors. I made 3 or 4 minus sign errors. There was one time I forgot I did a column error. I forgot to multiply an entry by neg4. I've 6 hours later, here I am. I've got it right. So let's do a 3D case. These are hard to do by hand. Do them by hand. If you do these in Word, I do it in Word because I have to teach you guys, which is great. I love teaching you all. But it's probably not a good idea to do just because. You probably want to do it on paper if you're a student. So let's find the inverse of this guy right here. 2, 3, 2, neg 1, 5, 6, 7, neg 4, 4. So let's find its inverse. So here we go. And again, the -1 means that's the inverse, but that's the denotation of the inverse. But what does it look like? Now, I couldn't get the matrix form of this to work. Like I wanted to wrap this in matrices. This little wimpy bar should look like it should look like this. Actually, it should look like this. But I want to squeeze everybody inside. So let's see if I can do that. Control X. Well, Control V. Yeah, actually, I guess, okay. That's cool. Okay. So I was able to, with some success, so here's what I want. I want to do this. You can think of this in a very real way as the identity. This is the identity I over here in 3D. And remember, you can only do inverses of square matrices if the matrix is indeed invertible in the first place. But you can only talk about inverses when you're doing square matrices. You can't do inverses of non-square matrices, okay? But anyway, and even among the square matrices, there are matrices that are non-invertible. But this one's going to be. But now, guys, here's the thing. You can think of this as I divided by A. You can think of the inverse, like if A is the original, you can think of this guy right here as I divided by A. The inverse, 1 over A. Cough, cough. You know, that informally speaking. So here's I divided by A, but we want to write this as A invert over I. So we want the I to go here and the A invert to go here, and we'll know what A invert looks like when A invert is here and I is here. Doing that, though, is the hard part. Now, remember, if you're off the main diagonal, which I've written in red, I want you to eventually become 0. So we're going to spend a lot of time and pain to make that happen, and I made a lot of mistakes along the way that I had to fix. So you can do it in a billion zillion different ways. Here's what I did. The 6 and the 2 look friendly at the time. I wound up making mistakes anyway. But what I did was I turned the 6 and the 2 into 12s. I actually got off to a good start. I turned the 6 and 2 into 12s, and I did row 1 minus row 2. I put it into row 2. I did row 1 minus row 3, and I put that into row 1. The most important thing to note is my puts. I put into row 2. I put into row 1. But why did I do my puts? Because that's where my red zeros need to be, here and here, right? So you got to do the puts in row 2 and row 1. Okay, so I got my red zeros. Everything else, for the time being, is collateral damage. So remember, anything you do to the whole row. So row 1, now when I'm talking row 1 minus row 2, I'm talking the old row 1 minus the old row 2, and that goes into the new row 2 down here. So 6 minus 0 is 6, and that goes here. 0 minus 2 is neg 2, that goes here. 0 minus 0 is, well, 0. Now, here, this is interesting. 12 minus neg 2 is 12 plus 2, which is 14, that goes here. 18 minus 10 is 8, that goes here, and so on, right? And 12, but hey, 12 minus 12 is 0. That's why we did this. That goes here. And, okay. And what else? Row 1 minus row 3, but I have to do my put in row 1. And you may ask, well, Jason, could I have done row 3 minus row 1? Sure, I just went about it this way. But you have what you don't have a choice on, you must do your put in row 1. Or at least if you went the way I went. Okay. So let's see. Now, row 1 minus row 3, 6 minus 0 doesn't change. So we're putting in row 1. Now, O minus 3 is neg 3. Neg 3 goes there. 12 minus 21 is neg 9, goes there. That's just collateral damage. 18 minus 12 is positive 30, goes there. Yeah, collateral damage. We ultimately want 0 there, but we just have to let it be, just so you don't mess up a red 0, it's okay. Now, 12 minus 12 is why we did this, to get 0 there. There we go. Now we want to clean up the house. We want to see how everybody's divisible by 3 on this row, and everybody is even divisible by 2 on this row, and on this row everybody is divisible by 3. Just clean up. You can divide a whole row by a constant if applicable. So divide row 1 by 3, which is multiplication by a third, and then for a half here on row 2 for another, and likewise for a third on row 3. Just clean house. You'll come back around. It just makes your numbers prettier. You don't have to, but it's an awfully good idea. Okay. Now, the next thing I want to do, my spacing got a little bad there. But now row 2 plus row 3, and I want to put on row 3, why? Why am I doing this? I want this negative 4 to die. Notice I've taken care of row vector. I've taken care of this solution, column vector, not row vector, column vector. I've taken care of this last solution, column vector. I've got my zeros here and here. Now I want to either get rid of neg 4 or 10. Hey, this neg 4 is awfully convenient. Let's kill this neg 4. So I'm going to add this pos 4 to the neg 4, and that will do it. That's why I'm doing row 2 plus row 3, and my motive is to get rid of the neg 4. So that's why I'm doing this. And, well, there I go. Now, there's a lot of collateral damage on the way. 3 plus 0 is 3. Neg 1 plus 0 is neg 1. 0 plus 1 is 1. 7 plus 7 is 14. That's gone. And 0 plus 4 is 4. And there I am. And I don't care. The only collateral damage that I can't have, that I can't allow, is to lose a red 0. That's the only forbidden collateral damage. Any other collateral damage is game. I can have it. It's fine. Now, 2 row 1. Now, here's the deal. Between 4 and 10, I need 20, the least common multiple. I need 20s, right? Let's see, and let me just the LCM of 4 and 10 is 20. I need to zap a 20, zap the red 20. That's where I'm heading with all this, right? So zap the red 20. So I multiply. What did I have? I had I multiply everybody by 2 here to make this 20, and by 5 down here. 4 times 5 is 20. So I get 4, 0, neg 2, neg 6, 20, and then times 5 down here, 15, neg 5, 0, 35, and of course 20, 0. Now we're not going to mess with row 3 for the time being. Now, so here we get our beloved 20s, and my spacing's a little bad. Microsoft is hard to control. So we get, well, now you could do row 2 minus row 1 if you'd rather, okay? But I'm going to do row 1 minus row 2, but you must do your put in row 1. And we wind up getting all this stuff, row 1 minus row 2, and I'm talking about the old row 1 up here, right, and the old row 2 up here, but you do the new row 1 is what I'm talking about here. So 4 minus 15 is neg 11, 0 minus a minus 5 is 5, neg 2 minus 0 is neg 2, neg 6 minus 35 is neg 41, collateral damage, 20 minus 20, that's why we're here. There's the 0. Now we got to make sure the collateral is faithful to my 0. 0 minus 0 doesn't harm it. So my 0 is not harmed. So no harm to my 0. Now, we clean house back up. I want to see how everybody's divisible by 5 here. Go ahead and divide back by 5, just to make things neat and petite. Now, looky here. Here's a row, a column. My column vector has been good here. Now it's good here. Guys, you don't know how many times I had to go through this to comb out my minus sign mistakes and my miscopies. It took me hours. I shouldn't admit that. But now let's look at this column. This is the last guy I've got to clean up. I'm making it look like this took me 5 minutes. That's the furthest thing from the truth that ever was. Now, 7 and neg 41 is not convenient. 7 and 14 is convenient because 7 times 2 is 14, right? Why didn't I do that first? Why on earth did I? Oh, no. Guys, I so should have got rid of that 14, shouldn't I? You know what? I made on my first time through, I forgot I made a miscopy, and I copied this 14 down as a 0 by mistake. That's why any person with if I'd had any common sense, I'd have got rid of this 14. But I made a miscopy, and I thought I was all. But anyway, I did the 41 first, so here we go. This is correct now. It's all correct, but you know, if it wasn't for my error, I would have done the 14 first. But it's okay. This is correct, albeit it's going to be the sort of the ice cold way to go. I'm going to cancel the neg 41. Now the neg 41 should be in red. Wait, no. I'm not going to cancel the neg 41. What am I talking about? I'm going to cancel the 7. The 7 is off diagonal. What's off diagonal? Either the 7 or 14 needs to go. I am going to cancel, well, I'm going to cancel the 7. And why on earth? I used the neg 41 to do it. Oh, no. That's because of that mistake I made. I tricked myself into thinking my 14 wasn't there anymore, and it's there. Well, let's proceed. It's correct. I guess if I evilly insist on using neg 41, 7 and neg 41. If we want to do it the hard way, we do 7. Here we go. 7 times row 1. You do 41 times row 2, and you'll get these ugly numbers. And then you'll get, naturally, you guys will be smart enough to do row 2 and row 3. But we'll get these ugly numbers, almost as ugly as my spacing at this point. And they're correct. I checked my answer against Wolfram Alpha. My whole answer is correct. Now, Then, why did I do this? Here it is. Sorry, here it is. It's all correct. Why did I do this? Because, well, I want the 287s to match. 7 times 41 is 287. These are the opposite signs. And so I want to add row 1 and row 2, but I got to do my put where the red is. Always do your put where your red is. So row 1 plus row 2, put that in row 2. And you'll get your 0 there. We did it the hard way, but cheers. Okay. And you'll get, well, neg 77 and 123 is 46. And then, yeah, we get our correct neg 6 there. We get neg 14 there, sure enough. The shoe fits. Well, eventually we would have had to face up to 41 anyway, so I guess it's just as well. It's kind of a pity I didn't exploit the 14 and the 7, but it was because I messed the problem up like 2 hours ago. Now, well, I've long since fixed it. Okay, and well, so we've taken care of that. Now there's still one more off diagonal got to go, and that's the 14. Well, we'd eventually had to face up anyway, but we got a clean house. I'm not going to deal with 287. We need to divide back by 7, and we need to divide row 2 by 2. So we got 41 back, and at least we got 82 back. At least it's a little better. Now, we need to multiply. 41 and 14 have no kinship, so I mess it back up a little bit. At least not as bad. It's going to be nasty, but it would have been nastier like this. So I do 41 times 14. I multiply this entire row 1 by 14 by 14 because it already had the 41. You hit the 41 by 14, but you got to hit everybody in this row by 14, as always, right? And then you multiply the 14 by 41 on the other hand, but you got to hit everybody by 41. Guys, a mistake I made, I forgot to hit the sweet little innocent 4 over here by 41. So that's 164. Don't forget him. Don't leave him out in the code. 0 doesn't care, but, well, so we got the guys on the left. Usually people don't miss it. The 4 is easy to miss. So hit everybody with 41. Now, we're not going to mess with row 2 at this time. So, well, we get our... Notice I didn't even evaluate this. I left it like this. So, it's going to be 574. But we don't care right now. We know that these, if we subtract, these are going to annihilate, and we're going to do the put call where the red guy is in row 3. So I did row 1 minus row 3. So we do, you're going to end up with this. I about ran out of room, but I was able to just make it on the board here. Now 41 times 14 is 574. But notice I left all these in strangled out form like this. I'm never really going to use 574 much. If I leave it out like this, it's easy to deal with. Notice you see the structures of 14s. And if you divide back, I divide everybody out by, I divide by 574, and that would be hard to deal with, except if I divide by 574, I'm dividing by the product of 41 and 14. So if I divide by the product of 41 and 14, here's how you do it. If you divide 11 and 14 by the product of 41 and 14, you're going to get 11 over 41 because the 14s are going to kill each other. So here's 11 over 41. I'm dividing by 574. So I'm going down here. Let's go down here. We're dividing row 1 by 574, which is 41 times 14. Okay. So we divide by 574. So 11 divided by 11 times 14 divided by 41 times 14. That's just 11 over 41. And then now neg 70 over 574 would be hard to deal with, but that's just neg 5 and 14 divided by 41 and 14. That's just neg 5 up top, 41 on the bottom. And then 28 over 574 would be ugly to deal with, but that's just 2 over 41. The 14s annihilate. See how much nicer that is? That's an arithmetic trick you can do. Okay, and then I just get, and then this is, now this divided by itself is 1. And then the zeros don't care what you know, they don't care about the 574. So we divided this whole row by 574. Now row 2, I divided by 82. Now does anything reduce? I don't believe so, because 23 and 82 don't have anything in common except 1, but that doesn't count. Neither do 3 and 82, neither do 7 and 82, so no reducing there. 31 and 164. Now I need to tell you. Now row 3 we divide by neg 164, so everything changes negativities. So it's neg 31 over 164, and there's no kinship there. 29 over 164, no kinship, and that's positive. Positive 13 over 164, no kinship. And then we want ones, because we want the identity over here to the right. Notice, guys, we have our beloved A inverse over I, right? And here's A inverse. We found it. Here it is. And I checked it against alpha, and it is correct. 6 hours later. Okay, yay. Now, so if we were to multiply these, we would get the identity. We would get, this is the identity, 100, 010, 001. That's what I mean when I say the identity, right? It's the 3 by 3 identity with ones on the main diagonal and zeros everywhere else. That's the identity. So, so in other words, if you let J, so J is this guy, right? Let's just say that J equals the original guy, the 2, 3, 2, so on and so on and so on guy, this 3 by 3 guy right here. If J is this guy, and then J invert would be this guy. But J times J invert is commutes. They commute, which equals J invert J, which equals the identity matrix I. We're referring to I as the identity. And the identity is just 100, 010, 001. Okay. Now, and keep in mind, remember the identity, for the identity, AI equals IA, which equals A. The identity acts like, you know, it just acts like the number 1 of multiplication in the real numbers. Well, guys, wow. Okay, we survived inverses, right? You gotta love inverses. And one thing we did in the class, I didn't want to spend a whole lot of time on it, was it's called the I'll do that next video. That's enough for this video, guys. Let's close this out. Thank y'all, and I'll talk about the expected value on maybe the next video. I'll see you guys.